Now we study the hierarchical model of clustering. So look at the basic definition of the cluster analysis, as we have seen that it should minimize the intra-cluster and maximize the inter-cluster distances. Now to understand the hierarchical clustering, it is here we are trying to produce a hierarchy based on the proximity between the various points. And hierarchical clustering can also be represented using a dendrogram, which is a tree-like structure that is showing the sequence of mergers that are happening. So as you can see here, these are the representing the points of merger or splits. If we are going from a single cluster and splitting, or if we are going from a n cluster where n is the number of points, then we need to do a merger. And if we are starting with a single cluster and dividing, then we need to do a split. And the strengths of the hierarchical clustering is, first thing is that it does not assume any particular number of clusters. So if you remember the k-means, the problem was that it assumes the number of clusters that are going to be finally created. And this is also represents the real world taxonomies in many areas. For example, as we can see, if we look at the animal kingdom, the taxonomy that is created is hierarchical. So it is that some species have much closer or highly proximal to some other species compared to the rest of these species. So in that sense, it has the natural ordering within this approach. And two broad approaches within the hierarchical clustering is, one is agglomerative. So here we are merging the clusters to create the hierarchy, and the other one is divisive. So here we are starting with a all-inclusive cluster and are splitting at every point till we reach the sufficient level of quality. And the hierarchical algorithms use a mechanism for proceeding further, and typically what they do is they build a matrix. Suppose there are n data points, they create an n by n matrix where they store either the similarity or the distances between the matrix. So that is between the points. So that is going to help in making a decision with respect to the merger or split. And the most popular or basic algorithm for the agglomeration is that we initially compute the proximity matrix for the entire data set we have, and then we start merging the closest clusters here, which is based on the proximity, and then we update the proximity matrix after the merger. So that is to say, we initially started with 5 data points, and once we merge 2 data points which are closest, so now we have got 4 clusters, because we started with 1 point in each cluster initially, and then as we merged, after the first merger it reduced to 4 clusters, and then we may do further mergers. But even before doing the further mergers, we need to recalculate the proximity matrix, because for the points that have been merged, we need to think in terms of how to calculate the proximity of this cluster with the other points or the other clusters. So one of the challenges is the computation of the proximity after every step. So the proximity matrix will look like this. Suppose here we have got 12 points. So there are going to be 12 rows and 12 columns to start with. But as we do the mergers, the sum of those columns and rows have to be combined, and then we need to recalculate the proximity matrix for the existing new number of clusters that we have. To start with, we have the 12 clusters, and we can see here that there are some natural clusters here. There are some which are very close, and they are very distant from the other points. So what happens is that when we do some mergers, we may reduce those 12 points into 5 clusters. So at this point, what we can see is that again we calculate the proximity. So it is reduced to 5 by 5 matrix. And here we realize that 2 and 5 are very close. Then what needs to be done? So we need to combine that, and then we need to recalculate the matrix by removing these values as they exist in the previous step. So we need to recompute the proximity matrix. Then we will have 4 clusters and then 4 by 4 matrix that is going to represent the proximity. And how do we calculate the proximity matrix? There are several measures which we can possibly use, and none of them are perfect. So what we can, in the sense that some of them are easy to measure or calculate, and some of them are very difficult to calculate but maybe more effective than the simple ones. So if we look at one of the simpler ones, it can be the minimum. So if we have 2 clusters, we need to look at the proximity between the clusters. Then what we do is that we look at 2 points which are representing the minimum distance between the 2 clusters. If we look at the actual points, it is possible that we will take these 2 points and we measure the distance between the 2, and we say that this is going to be the basis for determining the proximity and then taking a decision in the future on whether to merge the clusters or to keep them apart. And similarly, we can have the maximum, group average, and etc. So if we use the minimum, it looks somewhat like this. And then we are going to, at every step, we have to do between every 2 clusters. So we need to fill in this entire grid. That is important. So at any point, for example, here we have the 8 points. So what it means is that there are 2 clusters. So now it is reduced to 2 by 2. But assuming that there are some 10 points here, 10 clusters. So it is going to be 10 by 10 matrix. And in each case, that is going to represent the minimum distance. So instead of minimum, we can also take the maximum. So in that case, suppose that the clusters are like this. The maximum is that among the points. So this, as you can see here, these 2 points are representing the maximum distance that can exist between the 2 clusters. So that can be one way in which we can look at the potential for the merger of these clusters. Or we may take a group average. So a group average looks more meaningful, considering that we are looking at all the points and the distances, all the distances. But as you can see here, once we start doing it, the computational complexity is going to significantly increase. Once we have 100 points on this side, 100 points on that side, 2 clusters, we know that we need to consider thousands of distances before we can get the group average. Or we can think in terms of a centroid and then measure the distance. Then the challenge is to calculate the centroid first. We need to identify what is the mechanism whereby we find the centroid, and then we are going to determine the distance between the 2 centroids. And we may also have the other approaches which are based on some objective functions. So that function can consider all the attributes and can give appropriate weightages or the suitable normalizations, and then may think in terms of the or even the neighborhood may be considered before you consider the 2 clusters or proximal. So if we are considering, we are trying to do a hierarchical clustering using the minimum. So it is going to be, let's say we are looking at these 6 points. Then what is going to happen? First thing is that we are seeing that the distance between 3, 6 seems to be the minimum among all the distances that we see. This is, first we need to compute a 6 by 6 matrix. And when we compute the matrix, we will get the distance between 3 and 6 is the least. So that we are going to merge into a single cluster. Now we have 5 clusters. So we need to compute the 5 by 5 proximity matrix. And then we may realize that 2 and 5 have the minimum distance among them. And as you can see now we have got 4 clusters. So 1, 2, and then there are 2 other points which each of them is we can consider to start with a cluster by itself. So now if we are looking at the distance, so as you can see here, so we will look at these 2 clusters, the distance between 2 and 3, that seems to be smaller compared to any other distance. So it is likely that we are going to combine these 2. And then we are going to look at the minimum distance that exists for 1 and 4 with respect to points in this cluster 3. So that will lead us to join 4 because 4 seems to be closer to 3 than 1 to any other point. And then finally we are going to get a single cluster that combines all of that. That is it, the final step. So we will proceed and then we reach a set of a way in which we create a hierarchical clustering. So we will see what happens. We will first see what is the strength and weakness and then see what happens to these clustering if we take a different approach. So now let's say we take this kind of set of points where we can clearly see a natural clustering, and when we use the minimum distance measure, then we are getting the actual real clusters. So that is because there is the distance between it is taking the closest distance as the proximity measure. So it is going to separate itself into two distinct points because of the natural barrier that exists between the 2 points. And so it could create the cluster with a non-elliptical shape. And now let's see what happens if we have some noise points. So once there are some noise points, then we are depending still on the minimum distance. So these noise points are going to create or distort the minimum distance calculation when we do the proximity metrics. And so we are going to end up with an unreasonable clusters which don't seem to represent the natural clustering that we can see visually. So the problem is that it is very sensitive to the noise and outliers because it is going to consider the minimum distance with respect to every point, and some of them can be noise points. Let's now look at what happens if we take the max as the proximity measure. So now we are considering again here we are considering between 2 clusters the max, but to start with we are calculating the proximity matrix, and then we are going to start with the same set of clustering. So that is 3 and 6 because we are going for a clustering with the minimum distance points or the most proximal points. And then next one is also 2 and 5. And now we are considering what is again the distance between these 4 clusters based on the max criteria. So now if we want to measure the distance between 1 and 2, the points we take are not 2 and 3 but it is 5 and 6, because of which there is a significant distance between the cluster 1 and cluster 2. So instead of that, if we look at 4 and 1, they seem to be closer to these existing clusters. So we are going to have the third cluster which is combining the 4 with the point 4 with the cluster 1. And then we are going to combine similarly the 1 with the second cluster, and then we are going to have an overall cluster. So as we can see, once we change the distance similarity matrix between the clusters, then we are getting to a different set of hierarchical clusters. So in this case, this can handle noise better than what the min did, for the simple reason that we are considering the entire cluster when we are looking at the distance. For example, this cluster, it is insensitive to the noise which is much smaller than this. For example, though this noise point is there, what is happening is that this point, when it is looking at the distance with this point, this is getting actually in a way become negligible compared when it is doing the calculations, because we are looking at the overall size of the cluster, and then essentially in a way it is called a diameter of the cluster, and adding that when we are measuring the proximity measures. So the noise and the points have a lesser impact, but then it is having another type of problem. Here we are seeing 2 natural clusters, but what we can see is that this is, as we start with individual clusters and we create aggregations or the agglomerative approach to create the clusters, what happens is that for this it is fine. But here the distance between this point and this point is so high that if there is a cluster here and cluster here, it does not recognize that there is some relation between these two. So in that case, we are going to get unnatural clusters which are based on the max criteria for the proximity. The reason this happened is that the distance between these two is much smaller compared to the size of this cluster. So it could not recognize, considering the max criteria, that there is a natural clustering that is separating out these two. We can take a group average. In that case, we are going to get somewhat different. So we are going to compare it with the point that is in the center, and then now the center has shifted to here and this is here. So we are going to get a different set. So effectively what we are saying is that by using different proximity measures, we are going to get different forms of hierarchical clusters. So we will look at another simple approach that is used in the hierarchical clustering, which is a minimum spanning tree. So here what happens is that this is a tree, and minimum spanning, in that sense all the points are connected, and so we have a n points in the space, so we are going to get n minus 1 nodes. And what happens is that in this case here we start with any point, and at each point we are considering the closest point to this, and we are creating an edge, and thereby we are creating a spanning tree which is representing the edges to the closest. For example, for 2, it did not bother to create an edge with 1 because the 5 is closest. Similarly, at every point it is trying to create an edge with the closest point. And now we may be able to create clusters by identifying the edge which is representing a maximum distance. So if we break along that, we will get the two clusters. But as we can see here, this is again depending on only 1 point relationship. So if we are considering that there is one edge which is representing the maximum distance, so we break it along, we break the edge, then we are getting 2 clusters. Then we are not considering the relation between with the other points or the density of the points, etc. So in that situation, it will apply only when there is a uniform spread and there is a no distinct shape. So we may be able to get a cluster using this minimum spanning tree. And the minimum spanning tree algorithms look like that. It is relatively a simple algorithm and can work only in very restricted situations. So here what we do is that every point we create a minimum spanning tree to start with, and then we do a divisive hierarchical clustering in order to create the set of clusters. So what we do is that at every point we break the link corresponding to the largest distance, and then we are creating a new additional cluster. So we may do it until we have a singleton clusters remaining, or based on some other criteria we can stop division further, so that we are going to get set of clusters. And then we look at another popular clustering algorithm called chameleon. So this algorithm uses both agglomerative and divisive principles, and this is also uses the graph approach. So it is not using a tree, it is using a graph, and it increases the robustness of clustering by not going with a minimum spanning tree, but rather going with a graph which represents the k nearest neighborhood. So for any point, it is going to find the k nearest neighboring points, and it is going to create the edge between with each of those points. So thereby you are going to get a dense graph, which is compared to, for example, previously when there are n points, we were getting about n minus 1 edges. But if we take k as 2, we are going to approximately get n square edges when we have n points with the k nearest neighborhood graph. And after we create this graph, we can think in terms of partitioning again by cutting the edges which are representing the high distance. And then we can think in terms of the merger using another criteria. So the chameleon works like this. For each vertex of the graph represent a data object, and there is an edge will exist between two objects if the k most similar objects, if they belong to the k most similar objects. And then the edges are given weightages to reflect the similarity. And then it takes a partitioning algorithm whereby it thinks in terms of partitioning the graph such that every partition cuts the edges which have got a low correlation. So that is to say, low similarity between the connecting 2 points with the low similarity. And thereby we are ensuring that the similar points stay within the same cluster. And then next what we can do is that after that we can go with an agglomerative. If it creates too many clusters, we can think in terms of merging some of the clusters. While merging the clusters, we may consider again the points, we can consider the density of the connectivity of the points and then the closeness. Thereby we may be reaching more natural clusters. And the hierarchical clusterings can be at best take in order of n square if there are n number of points, because it has to calculate the proximity matrix. But considering that it needs to do multiple iterations and it needs to calculate the proximity matrix every time, so it may have a complexity of the order of n cube rather than n square. So with respect to the space, if we are depending on only on the proximity matrix, the n square is sufficient. But with respect to time, depending on the number of iterations we do, if the order of iterations is order of n, then we are likely to get n cube. But if we use some optimization and thereby we ensure that we don't need to do n iterations before we arrive at our clustering, we may be able to get this level of performance n square log n. And some of the problems with the hierarchical clustering is that whenever we make a decision to combine clusters, we do not undo here. So there is no objective function that we have which we are trying to minimize, and there can be sensitivity to the noise and outliers, as we can see based on some of the measures, and we have seen that some of the algorithms were, some of the proximity metrics were significantly influenced by the noise and outliers, because of which we could not get the natural clusters. And also there is a challenge with respect to using the different sized clusters. So as we have seen, two natural clusters, one much larger than the other, when we use the max as the distance for merging the clusters, we could not get the natural clusters. So these are some of the challenges we get when we use the hierarchical clustering.